Hello, I'd like to go over the Unit 5 Module 1 fundamental ideas worked out through these problems, and these problems have been posted. I suggest working through them and then using the video to grade yourself or to get further explanation. It's certainly not a substitute for doing the problems yourself. We did this problem very similar in class, so let's take a look. What we're going to do is we're just going to rank the potential energies here, and we know that the weakest bonds are going to have the highest potential energy. Strongest bonds will have the lowest potential energy, or the most stable, meaning the most amount of energy required to separate the particles. What we're going to do is use the same designation. The most stable, we'll put a circle around it. A triangle, we'll put the least stable. And so if we do that for these reactions, we see that several of them have a circle as a product and others have a triangle. What we're looking for is if the potential energy, if the triangle is above, meaning, okay, it is always going to be above the potential, it's always going to be the highest potential energy, and the circle is going to be the lowest. If the triangle is in the products, we expect it to be endothermic because the products now have the highest potential energy. And if the triangle is in the reactants, we expect this to be exothermic, meaning that we're making more stable products. So if we're looking for endothermic reactions, we see that B, C, and D all have triangles, all have higher potential energy products, and we would predict them to be endothermic. All right, in the next question, we're asked to do the same type of analysis, but with real elements involved. And so we're going to use the general principle here. We just substitute for the individual elements, we're substituting A and B, and we're looking for combinations of AA or BB because, okay, so we see that for A, we could write this as 2AB, making 2AA plus 3BB. Do the same thing for B. AB goes to AA plus BB. C is 2AB going to A2B2. And D is going to be AA plus 3 BBs going to 2 AB3s. And why do we want to do this? We want to do this because the general exothermic reaction is going to have AA as reactants and BB as products. Or an endothermic reaction is going to have AB as reactants and AA and BB as products. And so when we look at this, if we're looking for exothermic reactions, we know that A can't be true because AB is a reactant instead of a product. B can't be true because we have, again, AB as a product. C is going to be true because we have two particles going to one particle, so we know that an extra bond is made that has to be exothermic. And D is true because we do have the AB as the product, so we would pick the answers to be C and D. It's really important to feel comfortable using the AA-AB energy analysis. It's really going to come up in a lot of activities and on exams. Here we have the same type of question, but now we have a diagram that we need to determine. So if we converted the chemical reaction into AA and AB, we see we have 2AB plus BB to make 2AB2. Keep in mind that AB are just generic designations. We're just looking for the high potential energy content of the AA or BB bonds. We see that the reactants have high potential energy, the products have all AB bonds, so we would expect this to be an exothermic reaction, and we would pick C, given that the reactants would have the highest potential energy. This is a problem from the homework set. So we're looking at the burning of methane to make CO2 and water, and we're asked some questions about the configurations and the potential energy change and the temperature effects. So to do that, we need to get the sign of the change in potential energy and the change in configuration. So if we were going to write this in that notation, we see that we have two ABs reacting with three BBs to make 2AB plus 4AB. So we see that we have many more AB bonds in the products. The reactants are expected to have high potential energy due to the 3BB bonds. So we'd expect this to be exothermic. Delta H will be less than 0. The potential energy of the products are lower. If we're doing the configuration analysis, we have 2 gas particles plus 3 gas particles, making 2 gas particles plus 4 liquid particles. That means we have 5 gas particles going to 2 gas particles. Keep in mind configurations, we treat the gas particles as the most significant in terms of determining the overall effect. We see that the configurations are highest in the reactants and they go down with the products. If we want to answer the temperature dependence, we make a PEC diagram where we show exothermic behavior first. So what I do is I put the R and the P first just to assign the correct potential energy ordering. And then since P has less configurations, I'm going to shift it to the left. And then the R, which the reactants have higher configurations with 5 gas particles, would be to the right. So in this case, we see that what is favored at low temperatures is the bottom left. And so that would be products. And so products are favored at low temperatures. That would be true. B is true. What's not true is A, that the reactants have lower potential energy. So A is wrong, but B is right. C is wrong because we do not expect this to become more product favored at high temperatures. We expect it to become reactant favored, which is why it's in the top right. Potential energy of the products is lower than the potential energy of the reactants. That's true. It's true for every exothermic reaction. And the reactants can adopt a higher number of configurations. That's true. We already did that analysis, and that means F is wrong. So we would pick the answers E, D, and B. These are the types of questions that you're going to be asked in the homework and will be on multiple choice portions of the exam coming up. All right, if we want to answer this question, which reactions have delta S as positive, we want to make sure that we realize what happens when delta S for a reaction is positive. It means that the reactants have less configurations and they make products where they have more configurations. So that's what delta S is positive. A can't be true. We can't have 3 gas particles make 2. That means delta S would be negative, so A is wrong. B, we can't have 3 gas particles make a liquid. That delta S is also negative. Less configurations in the products. That's not what we want. We want greater configurations in the products. That is true in C, where we have 1 gas particle making 2. That definitely has a delta S that's positive. And 1 solid particle going to 1 solid particle plus a gas particle. That is true. So the answers here would be C and D. Which of the reactions will have delta S as negative? Now we have the opposite case. That means when we look at the reaction, reactants and products, reactants have high numbers of configurations, meaning more gas particles, versus the products, which have low configurations. That means these will have less. So delta S is characteristic of a delta S that is negative. If we look at the chemical reactions, A is definitely wrong. We can't have 4 gas particles make 5. That would be delta S is positive, so A is wrong. B, we can't have solids make a gas. That delta S is definitely positive. C is true. We could have 2 gas particles make 1 gas particle. There's an overall net reduction in configurations. That means delta S would be negative for C. And D, we have 2 gas particles going to 1 gas particle. That would definitely be true. The products here would have less configurations. Here we're asked to construct the E versus S curve. So we want to have potential energy in the y-axis, the entropy or the changing configurations on the x-axis. So we do our standard energy and evaluation to get the sign of the change in potential energy. We have AA plus 3 BBs to make 2 AB3s. So we see this is an exothermic reaction. Delta H is less than 0. We have 1 gas plus 3 gas going to 2 gas. The overall effect is that the configurations go down and the products, so that means S is going to decrease. So we rank the exothermic as R above then P. Since the products have less configurations, less gas particles, we shift the P over to less configurations, R to the high configuration state, and we see the answer is consistent with B. This curve is really important to identify based on the chemical reaction and phase information given. Here we have a chemical reaction. We're going to be asked questions about delta H and delta S. So we'll start with delta H. We just write this in our standard AB configuration. We see that the reactants have high potential energies with AA and BB. The products have AB bonds. We expect that to be lower potential energy. Expect the reaction to be exothermic or delta H less than 0. When we do the phase analysis, we see that there's 4 solid plus 3 gas to make 2 solids. Overall, the effect is that the number of configurations decrease. They go down. We expect delta S to be less than 0. So the products definitely don't have more configurations, so A is wrong, and delta H is not greater than 0, so that's wrong. Delta H less than 0, that's true, but the products do not have more configurations, so B is wrong. C has both the correct sign for delta H and the less number of configurations in the products, so C is true. D is wrong. Delta H is not greater than 0. E is true because delta H is less than 0, delta S is less than 0, so E is true, and that makes F wrong. So the answers are C and E. Okay, in this question, we're asked to analyze a chemical reaction of CO2 reacting with 4H2 in the gas phase. Everything's in the gas phase. This is consistent with many of the activities we did in class, just to sort of organize our thoughts. Keep in mind that what's in bold is the primary consideration. What's not in bold is the secondary consideration. We only use the secondary consideration when the primary consideration cannot determine directionality. Primary consideration for entropy is the multi-particle phase, and the secondary consideration are the single particle mass complexity. So by doing this, we see that this is a product-favored reaction expected due to the AA bonds, high potential energy in the reactants. In the multi-particle IMF, we expect water to be the most stable interaction with itself due to hydrogen bonding, so we would pick reactants. Due to the intermolecular forces, it probably has the highest intermolecular forces of all the particles shown. Entropy, we would expect reactants to be most favored due to the total number of gas particles, which is 5 in the reactants versus only 3 gas particles. And at the single particle level, we'd expect products to be more favored due to the average mass complexity to be higher in the products, given that the reactants have 4 out of the 5 particles are very, very simple. So these are the arguments we would make: 5 gas in the reactants versus 3 gas. Remember, entropy is always more stable and at higher number of configurations, so that would be with the 5 gas particles. Average mass, we would choose products. And the AA bonds in the reactants is why we would choose the primary products for energetics. That means here that we have primary considerations have been determined and they are different, right? So the primary are different. That means there's going to be a temperature dependence on directionality. This table best describes the trend with mass and complexity. Given that all the phases are identical, we're looking at a secondary effect. Secondary effect, which is mass complexity of the individual particle, since they all have the same phase. We see that as the mass complexity increases, so does the entropy. The best answer for that is C. So let's look at an overview for delta H. We have endothermic behavior and exothermic behavior. Keep in mind that reactants and products have different potential energies and they lead to this type of phenomenon. We're going to concern ourselves with the sign, where AA bonds would be present and where AB bonds would be present. So the sign of delta H for endothermic is positive, the sign for exothermic is negative. In an endothermic reaction, AA bonds are products. In an exothermic reaction, AA bonds are reactants. For an endothermic reaction, AB bonds, if they're the dominant trend, will be reactants. And for an exothermic reaction, AB bonds will be exothermic. Or exothermic reactions will have AB bonds as products. For a review of entropy, the sign, if the change of delta S is positive versus negative, that means if it's positive, that means the reactants have low numbers of configurations. If the delta S is negative, the reactants have high numbers of configurations. In a positive sign of delta S, reactants go from low configurations to products that have higher configurations, while negative sign means the reactants that have high configurations go to products that have low configurations. So it's really important to make sure that you can identify the correct sign for delta S based on this type of trend you see. There are more gas particles in the reactants than there are in the products. You know delta S is negative. If there are more gas particles in the products than the reactants, we would definitely pick the positive delta S. The best thing to do is to practice. Now here's a review on PEC diagrams or energy versus S curves. Just keep in mind there are 4 quadrants. There's the always favored, meaning it doesn't matter at what temperature the reaction is run, it will always be product favored. Then the top right, the species that's there, means that it is never favored. It doesn't matter what temperature you run the reaction, whatever's in the top left quadrant is never favored. In the top right quadrant, this species, if something is there, has been identified there, that means that it is favored at high temperatures. And in the bottom left, it is favored at low temperatures. So if we look at increasing temperature, we always access the high potential energy state. That means that if we have the curve, so we always access the high potential energy state. So if we have this case, directionality does change with temperature, meaning we make more product at high temperatures, and we actually make more product than we have reactants as we increase temperature. While in this potential energy curve, we also make more products as we increase temperature, but we never make more products than we have reactants because it is in the never favored category of products. And so in this case, even though we make a little bit more products than we did at lower temperatures, reactants, which is what's always favored, is what it will overall be favored, right? So just keep in mind these are 2 very important graphs that you should be able to walk through. One has directionality that changes and one that does not have directionality change. Both make more products as you increase temperature, but in one case directionality changes and in the next case it does not. If you keep that in mind, you should be able to answer all the questions we're going to ask you in terms of energy versus S curves on the exam.